Give me a second. Okay, good afternoon, everybody. My name is Samayo, and I'll be presenting on swarm intelligence. So this is going to be the outline or table of content I'll be running through for this my presentation. I would like to walk you through the definition of swarm intelligence, and then we'll look at two common algorithms in swarm intelligence, and then we'll look at advantages and disadvantages of swarm intelligence, and then we'll look at recent developments in swarm intelligence, and finally, we'll look at limitations in swarm intelligence. Before I go on, I'd like to uh, demystify the knowledge of swarm so we can have that base knowledge as we go on. So a swarm can be considered as a loosely structured collection of interacting agents. So basically an agent, when we say an agent, we are referring to individuals that belong to a group. They don't necessarily have to be identical. We're also referring to individuals within the group that contribute and benefit from the same group, and then individuals within a group that recognize, communicate, and or interact with each other in that group. So examples of swarm in nature, a classical example is a swarm of bees. Other examples that we can draw insight from when we talk about swarms is an ant colony, where the agent in that swarm is ants. And then we'll talk about flock of birds, the agent are birds. And then we'll talk about traffic as a swarm, the agents are cars. We'll talk about crowd as a swarm, the agents are humans. And then our immune system, which as a swarm, the agents are cells and molecules. Okay, that should be 140. So swarm intelligence is an emerging field of biologically inspired artificial intelligence. It is based on the behavioral models of social insects such as ants, bees, wasps, termites, fishes, and the likes. So also, we can look at it and say it is an artificial intelligence technique that is based on the collective behavior in decentralized, self-organized systems that is generally made up of agents who are interacting with each other and the environment. So if you look at how we looked at swarm and agents from this our previous example here, we can draw insight from there to understand that. Okay, so I don't know where you guys lost me. Hello.
You can just continue.
Okay, so when we talk about swarm intelligence as an artificial intelligence technique that is biologically inspired. So when we talk about agents within swarm intelligence, we are referring to individuals who are interacting with each other and also interacting with the environment. So conceptually, when we talk about swarm intelligence, we are referring to a collective behavior of a decentralized, self-organized systems, whether it is natural or artificial. Okay, and when we talk about decentralized, we are referring to something that has no central control structure. For example, when we say crypto is a perfect example of a decentralized system where nobody has a central control over everything. It is just causation and reaction. Okay, one feeding on the other, one responding to each other. Like when I buy crypto from you and I sell crypto from you and the likes. So it has no central control system. Everyone is just interacting and achieving a common goal uniformly. Okay, so and it's also based on group behavior found in nature. All right, so I'd like to walk you through principles of swarm intelligence. Some refer to it as features of swarm intelligence, but largely we are also referring to the same thing. We talk about awareness in a swarm intelligence system. There's awareness of each agent within the system. Autonomy, there is autonomous reaction within the system. Everyone has individual control of their own action. When we talk about decentralized system, there's solidarity within the system. There's expandability. The system has the ability to upscale and downscale. And there's resilience, which means the system has the ability to come back from tension control. So then let's look at two common algorithms in swarm intelligence, the ant colony optimization and the particle swarm optimization. So ant colony optimization can be considered as a study of artificial intelligence system, or let me just say artificial systems rather. modeled after the behavior of real ant colony. So when we say ant colony optimization, it's just using the base source as a referral in the term. So ant colony optimization from behavioral monitoring of ants. So it's modeled as an artificial system that is modeled after the behavior of real ant colonies and are useful as a probabilistic technique in solving this discrete optimization problem. So let me give a breakdown of what I mean when I say probabilistic technique in solving discrete optimization problem. So when we say probabilistic technique, we are saying that a technique that is wrapped around the probability state where there is n um, where there is n possibility for an x outcome. All right, for an x event, there's n possibilities. And then probabilistic technique in solving discrete optimization problem. So when we say a problem is discrete optimizable or is optimizable as a discrete problem, we're referring to an optimization problem that is controlled within a discrete variables and as objects or such as integers, permutation, okay, that can be found as countable sets. So you can borrow the analogy from discrete variable and continuous variable. You know, when we say continuous variable, we are talking about something with n infinity. Okay, variables like 1.1, 1.2, 1.3, you know, it's largely uncountable if you look at it. But if we talk about discrete, we talk about something that is whole. For example, integers 1, 2, 3, 4, 5, 6. So when we say we are solving a discrete optimization problem, we're talking about optimization, which is looking for the quickest position or quickest solution to a problem, and then we are using discrete variables as our base variables for finding the solution to those problems. All right, so ant colony optimization, for recap, ant colony optimization is a study of artificial system that is modeled after ant behavior and are useful for solving probability and as used as a probability technique for solving discrete optimization problem. So I'll give this a thorough breakdown as we go on with the slide with visuals so we can really understand what I mean when I say probability technique and when I say discrete optimization problem. So ant colony optimization, ongoing, I may say ACO. When I say ACO, I'm actually referring to ant colony optimization problem. So ACO as a technique has strong application in traveling salesman problem and several NP-hard problems. When I say NP, that's non-deterministic binomial time problem. Okay, so when I say traveling salesman, all right, so traveling salesman is just a terminology that is used to wrap around equations or problems. No, not equations, problems rather. Problems that require you to find the shortest path to solving it. Okay, for example, let's say you're given a list of cities with distances between each of those cities, and you have to find the shortest possible route to those cities from your own origin, to and fro. Let's say you're moving from, let me use Lagos as an example, you're moving from Akoka to Ikeja, for example, and you need to find the shortest possible route from Akoka to Ikeja. You know, that's a traveling salesman problem, right? So there are other problems like that. Ant colony optimization is a very useful optimization technique for solving those kind of problems, and also for solving NP-hard problems. So when we say NP-hard, we're talking about non-deterministic binomial time problems, and these kind of problems are when we say NP, that's non-deterministic. Their outcomes can give different variables. So let me do that by explaining deterministic and non-deterministic. So when we say deterministic, we say that if we're given X input, the output will always remain X. The output is kind of static. When we say non-deterministic, we mean giving X input, the output will always vary. Let's say for first trial, X may give you X, second trial, X may give you XY, and the likes and the likes. So the output is always varying. So when we say non-deterministic and deterministic, the output within both of them is always varying. So I'll move on. So in ant colony optimization problem, in ant colony optimization, as a technique in swarm intelligence, a set of software agents are designed as artificial ants, and they communicate based on pheromone models. Okay, and so largely pheromone models are used by real ants to mark their paths. Ants follow these paths as trade following behaviors. Okay, and then the optimization problem may be written in form of path finding with a weighted graph, and the constraint of a problem is resolved by using heuristics of ants. So when we talk about weighted graph, when I say the optimization problem can be written in form of finding paths with a weighted graph, when we look at ant trails and the way they follow, it kind of draws out a graphical model. All right, and each position within that graphical model, each ant's position within that graphical model is considered to have a weight. So that's why we say finding path with a weighted graph. So each position within that graph tend to add a weight, tend to have a weight relative to the position of that ant to the target and from the origin. All right. So when we also say heuristics of an ant, heuristics refer to drawing technique or behavioral pattern from a particular element. So the ant colony optimization is drawing a solution to problems based on the behavioral pattern of ants themselves. So this is a theoretical outline of how ants tend to solve their complex problems. So in achieving ACO, that's ant colony optimization, scientists began by modeling the simple behavior of ants, which led to the study of how these models could be combined and produce better results, better than individual models. Okay, so Dr. Zain was mentioning something, Mr. Zain was mentioning something earlier about evolutionary algorithms. So in course of my research, I realized that evolutionary algorithms shared close resemblance with swarm intelligence, because swarm intelligence largely is bringing different agents together to optimize their workflow or optimize their pattern uniformly, and to achieve this, they tend to produce more better results when they come together than when they work individually as individual models. Okay, so drawing this pattern from ants as an insect, scientists discovered that by modeling this behavior, they're able to provide solution to finding short distance to problems. And so largely it will interest you that insects have very few hundred cells. However, they have been well known or best known for their architectural marvel. I saw, and because of my research, I saw archaeologists unearth a massive ant nest in the desert. It was so massive I couldn't measure it, but it looked largely like the size of a duplex under the earth. So they are known for their architectural marvel, and they're also known for their complex communication system and their resistance to hazard in nature. Recall that we mentioned resilience as one of the features of swarm intelligence. So I also want to interest you to know that the way ants find their food in the shortest path is quite interesting, because ants are largely blind, and ants hide pheromones to remember their path. So for each ant moving along on a trail, they drop pheromone scents on the path so that they can all keep moving on that same path. But their pheromones evaporate with time. So whenever an ant finds food, it marks its return journey with the pheromone. And since the pheromone evaporates faster, the ants are to optimize with using the shortest path technique to ensure that they can return to the origin and back to the food source without losing trail scent. Okay, so the shortest path is actually reinforced by these pheromones. So if you look at the diagram I have here, you find that on the first diagram, top left, you find the nest and the food and the ants moving on a single path. And then there's an obstacle within the path, and the ants before the obstacle and after the obstacle are thrown into confusion because they can no longer find the path. But given n number of times, through continuous iteration, you find out that the ants within the colony tend to find the shortest path that can go around the obstacle. And once they find that shortest path, they ditch the longer path and go to the shorter path. And therefore, as they go to the shorter path, they enforce the pheromone model, or they enforce the pheromone scent on the tail of that shorter path, making it the most likely path for every other. By the scent of the pheromone, the return from the longer path, which is on my bottom left, and reinforcement to the top right, which is the shortest path, becomes a probability model, because what are the chances that the ants who are already deviating and following the longer path will return to following the shorter path? All right, and then that's where the theory of ant colony optimization was derived from. So this is a flow chart that that depicts or shows the typical flow of the algorithm within the ant colony optimization use as a swarm intelligence technique. So you find the start. So after the start, there's an iteration on the count, and then the shortest length is set to 0, best solution is set to 0, and then the ants are initialized. So each ant goes ahead, since they are moving at random, they go ahead to find the route to optimize the shortest path over the obstacle. And after doing that, once they find the shortest path to the obstacle, they update the shortest path. So if I also put it as correlation with the biological analogy I made earlier, you find out that from top left, which is the next to the food, to the right where there's an obstacle, so the ants are initialized in the top left, and then to the next one, there's an obstacle, so they need to optimize. And then once there's an obstacle and they need to optimize, you come down to the top left, the bottom left rather, and then they find the shortest path. Okay, so when they find the shortest path, they need to update the shortest path length, and then also update it as the best solution. And then from there, they can now form the pheromone matrix for every other ant to follow. And then that's where you find the shortest path being used as the base model for solving the problem of getting food to the nest. So in a situation like this, where after finding the shortest path and incrementing iteration, it is not still taken to the end, which is where the food source is, it goes back again, and all the ants again are initialized, and everybody starts finding the shortest path. So it's an iterative process, a continuous iterative process, until the shortest path is found that can link to the food, and then the solution tends to be solved. All right, so I think I missed something. Okay. So let's look at the application of ACO in scenarios. So ACO has found great use in vehicle routing with time window constraints, network routing problems, assembly line balancing, and also in data mining. So a classical real example of ACO is in snowbots, developed by Sandia National Laboratories in the US. And it can be used to locate victims in snow 4 times faster than humans using the ant colony optimization technique. All right. And then it's also used as transportation firms to optimize their route for delivery. Okay, so now let's look at PSO, particle swarm optimization, another optimization technique in swarm intelligence. So PSO is a population-based stochastic optimization technique. It is widely used for searching for an optimal solution in the computable search space. It was developed in 1995 by Dr. Albert Hart and Dr. Kennedy, and it was inspired from swarms of bees, flocks of birds, school of fishes, and the likes. Now let's look at some assumptions of PSO, particle swarm optimization. So the assumptions are each particle is searching for the optimum. And so optimum is, I'm not an English major, but optimum is derived from optimal, which is finding the quickest, using the quickest possible action to providing a solution to a problem. And each particle is moving and hence has a velocity. Each particle remembers the position it was in and where it had its best so far. This is referred to as personal best. And the particle in the swarm cooperate. They exchange information and about what they've discovered in the places they have visited. So when we talk about cooperation as an assumption in PSO, we are referring to that a particle has a neighborhood associated with it. So that's when we say it remembers its position. All right. So it has a neighborhood associated with it. A particle also knows the fitness of those in its neighborhood and uses the position of the one with the best fitness. Okay, so this position is simply used to adjust the particle's own velocity. And in PSO, individuals strive to improve themselves and often achieve this by observing and imitating their closest neighbors. It has also one operation, which is basically its velocity, all right, which is a vector number that are added to the position coordinate to move an individual. So let me make a simple scenario to emphasize more on the particle swarm optimization algorithm as swarm intelligence. Okay, so let's look at a group of birds trying to find food. So a group of birds are randomly searching for food in a given area, and there's only one piece of food in this area. Now, all the birds don't know where the food is, but they know how far the food is through each iteration that they have as they move around and look for the food. So what's the best strategy to find the food? The effective way is to follow the bird which is nearest to the food. Now, if you look at this, I've made some word bold because they can be easily referred to from my previous slide here when we look at the assumptions of particle swarm optimization. Okay, so when we talk about a group of birds, we are referring to a swarm, all right? Particles in a swarm. So group of birds refer to the swarm. And when we say they are randomly searching, okay, we talk about they are always searching, okay? So the assumption is that each particle in the swarm are always searching, all right? So when we talk about the given area, if you look at the definition right here for particle swarm intelligence, you find out that it is always used in looking for the optimal solution in a computable search space. So the search space can be any area. All right, I'll give an example as we go on of how this can be applied in real life as a search space. So there's always the assumption is that there's always a space that these particles are always contained in for them to achieve their objective. All right, so and there's one food in this area which indicates the target, and all the birds don't know where the food is, but they know how far they are from the food, which is they are searching for the optimum. And then the effective way is to follow the bird which is nearest to the food. Now, if you recall, I mentioned earlier that each bird updates particle, let me know, is bird. We could use bird as an analogy, but I'd like to use the base, which is particle. Each particle adjusts its own weight. The weight is a matrix of its own position by its environment. Updates its own weight by how close its nearest neighbor, which is closest to the food, is. All right, so it adjusts itself and improves its own self by observing and imitating its closest neighbor, which is closest to the food. So it's normally a chain of reaction. One bird who is closest to the bird with the food is imitated by another bird, which is imitated by another bird, as they all now closely monitor and find where the food is. All right, so I'll go on. So this is a flowchart that the natural flow of the PSO algorithm. So there's a start and there's an initialization of the algorithm parameters and the current swarm position, and then the calculation of the fitness of each particle, which is its velocity by its environment, and then there's a p-best, which is the particle's own fitness in its own environment and the group's own fitness to its own environment relative to the target. All right, so then everybody goes into a random search. Every agent within the swarm goes into a random search to achieve the goal. All right, so and each of these agents within the swarm keep updating their position based on the agent that is closest to the target. All right, so they keep achieving this, they keep doing this until they keep updating it until they all get to the source. And if they don't get to the source, they return back to calculate their own fitness and keep updating their p-best and their g-best. Okay, so when we say p-best, we are referring to the calculation of how close each article is to the target. And then g-best is how close is the group in itself close to its target. So this is the pseudocode algorithm for particle swarm optimization. So where it begins, then each particle in the swarm initializes its position and velocity randomly. And then once that is done, each particle in the swarm calculates its own fitness, all right, and the objective of the collective objective of the team is always better than the personal fitness value of each of the team. And then this is continuously updated as an iterative process. And then if you come down to the from, you see from all the particles or neighborhoods, it chooses the the p best value as the it chooses its best value as the group's best, and then it keeps updating its velocity and its speed until collectively every agent in the swarm gets to the target. So let's look at applications of particle swarm optimization. All right, so you find it in human tremor analysis, you find it in human performance assessment, you find it in ingredient mix optimization, and you also find it in evolving neural networks to solve problems. Okay, so this particular last evolving neural network is related to what Mr. Zayo mentioned earlier when he said when you're working in a very large team and there is in a very large team and there are many large models, you find out that your base optimization technique becomes lesser of a choice, and then you have to look out for bigger techniques. So let's look at real world application of particle swarm optimization. So if you find a close example in behavioral animation, okay. So the particle swarm technology concept is applied or currently being applied rather in computer graphics area, and was popularly used in famous movies such as Batman Returns in 1992 for DC lovers, and then The Lion King 1994, and From Dusk to Dawn 1996. But the most impressive usage of the particle swarm optimization is in the trilogy of The Lord of the Ring, where about 250 individual characters were simulated. Okay, so this was done using a computer software called Massive, which means Multiple End Simulation System Virtual Environment. It was developed by Steven Regelos for visual effects in industries, and it was used and it's being used in film industry for crowd and battle scenes. This particular software based on PSO actually won a Guinness World Record based on its usage role in Lords of the Ring, and where digital animation was combined with AI to achieve simulation fight of 250,000 individual characters. All right, so let's look at advantages of swarm intelligence. One good advantage of swarm intelligence is that it is scalable, it is flexible, it is robust, and the system is able to adapt to new situations easily. And of course, we can't do that without looking at the cons of swarm intelligence. One major con is non-optimal, which means that because the system is highly redundant and have no sometimes, and allocation of resources is not efficient, and which means duplication of effort is always rampant within the swarm. Okay, it is uncontrollable, so sometimes it can be difficult to exercise control over a swarm. They are likely to go haywire since it's a decentralized system, and sometimes it can be difficult to put things under lock and key. Okay, so I'd like to look at one or two more slides before I wrap up my presentation. And I would like to look at the application of swarm intelligence in robotics, which is called swarm robotics. Okay, so swarm robotics is the application of swarm intelligence in robotics. It's practically a group of simple small robots that can only communicate locally and operate in a biological inspired manner. Okay, so swarm intelligence robots are used in many fields: manufacturing, spacecraft, inspection, medicine, agriculture, and the likes and the likes. It is actually still a developing area, the same as swarm intelligence. So let's look at some recent developments in swarm intelligence. The US military uses it for unmanned vehicle control. NASA uses it for planetary mapping. Medical research uses it as nanobots to fight cancer. And swarm intelligence techniques are used for load balancing in telecommunication networks. Excuse me. And entertainment industry uses it for battle and crowd scenes. All right, so what are the limitations in swarm intelligence as a field in AI? It is still very theoretical in knowledge, and it has no clear boundaries as at now. The details of the inner working of insect swarm is still unknown, so it cannot be fully bragged on being based on the architectural workings or behavioral behavioral pattern or measures of insects. So, and the future of swarm intelligence is, of course, still emerging. All right, before I close, I would like to crave your indulgence to watch this very brief video. I find it very interesting, and I see it as a clear example of swarm intelligence in action. Please enjoy it. I see it appearing as frame by frame on my phone. I hope it's not frame by frame on your end, please.
Yes, I was going to actually say that it
Ah,
doesn't appear like a full video
okay.
progression.
Okay, so sorry about that. Let me just. I see it on my phone showing as frame by frame, so I thought it may be doing the same for everyone as well. Okay, so let me just quickly. All right, so I'll stop here and I'd like to take questions. Thank you.
Okay, wow, that's a very good one. Thank you very much, Samuel, for that presentation. I already have loads of questions. I'm just wondering how I'm going to how I'm going to do this to not take another 1 hour, like in the case of Precious. So I will just give room now for questions from everyone else. So if you guys have your questions, you can go ahead, shoot him your questions, and I'll be checking his responses to the questions. Any questions for him? In the absence of questions, Mr. Samuel, please let's go to your slide so that we get started. I have nothing, not
Okay,
so
sir.
much to talk about your slide itself. the slide structure because you already have some experience using a slide template, so you don't have much of a problem. So I guess I'll just go straight into other things.
I'm set, sir.
Okay. Yeah. So your presentation was really good, and I want to just, of course, I'll ask a couple of questions. We'll go over your slides from the beginning. So let's go to the next slide.
I'm on the next slide, sir.
Okay, I can see that
Hello.
now. All right. So of course, it's good it started from what a swarm is. Before we now talk about what swarm intelligence is. And I think I like the fact that you also used AI terminology here, or at least the computer relatable terminology, which is agents. Okay, because if you talk about if you just talk about individual organisms or something like that, it's more biology than AI. And our goal of studying swarm intelligence, of course, we're dealing with algorithms for AI. So our goal is to see how biologically inspired um, procedures, how we can build, how we can design AI algorithms from such procedures. So let's move on to your next slide, um, where I think my question starts from. Okay, not this, the next one. So just like in the case of pressures, I'm more interested in how we can bring this down or narrow this down to AI. Because when you say swarm intelligence, of course, you know that we are dealing with something that comes from biology. And just as mentioned, the applications are quite wide. But in the study of intelligent systems, in building intelligent agents, how do we really apply all these notions to realize intelligent agent-based systems? So that's one of the things I'll be doing in this component of the session is to walk you through narrowing down the entire thing to to AI systems, so that we don't just have you know biology terminologies and you know notions adapted from biology, but generalized to all types of systems or all various application areas. But now I want to look specifically at how this works in artificial intelligence. So before I go ahead asking you some questions from some of your slides, I will just mention something. So, when you're talking about swarms, um, how do you identify or what are the notions that tell you should I say
Can anybody hear me? Hello?
I can hear you. I can hear you.
Okay.
Yes, I can hear you.
can you hear me now?
Yes, I can hear you now, sir.
Okay, so what are the properties you consider to to identify that this is a swarm? Okay, what properties are characteristics or what properties are exhibited by swarms? Because you've go back to your definition of a swarm. You've defined what a swarm is, okay, But now I'm also interested in saying, are there specific properties that indicate that this is a swarm? Because it's those properties that will be like the axioms for building swarm-inspired AI algorithms. So identifying these properties, we need to drive them home to AI systems now as fundamental axioms for developing the procedures and algorithms in order to carry out the optimization processes. So are there properties you would use to identify the collective behavior um, exhibited by swarms?
All right, so for that, I would like to bring you down to slide 6 that talks about the principles of swarm intelligence. And this that I
Okay,
see
very good.
as a base point to elaborate, provide answer to your question. So when we talk about establishing or creating or designing a swarm intelligence system, then we should take into consideration that each agent within the swarm intelligence system have to first and foremost be aware. They, in as much as they are swarms, agents within a swarm, they all own their own autonomy, which means they have the ability to personally carry out their own actions. If you look at how we analyzed particle swarm optimization, find out that each agent within the particle swarm has the ability to optimize its own p-best, which its own fitness based on its own velocity. So each agent, while designing a swarm intelligence system, you should take into consideration the following characteristics: that each agent shares its own cognitive awareness of the target source and the solution to that particular problem. Each agent is also autonomous, which means they have the ability to carry out their own action. So I also want to draw reference also to ACO, anti-colony optimization, where if we are to, if, which is designed based on wheel ant behavioral monitoring. Each ant within a colony, despite functioning together as a group or as a collective, as a collection, they also possess the ability to individually create their own paths using pheromones. So each agent, while designing a swarm intelligence system, characteristics align with the principles of swarm intelligence, which is each agent has to be self-aware, each agent has to share autonomous, each agent has to be resilient, each agent has to have the ability to expand. So I'll draw that example from PSO, also particle swarm optimization, where each bird, for my example, has the ability to optimize its own velocity based on the closest neighbor to it. So it can decrease its velocity based on the closest neighbor and increase its velocity based on the closest neighbor. I don't know if I answered the question, sir.
Yes, thank you very much for that.
I
All
can't
right.
hear you.
Yeah, my mic was on from the two sides, which is why you would have that echo earlier. So thank you, Nice, for pointing that out. Now, when we're talking about uh, um, the principles of swarm intelligence, you correctly answered. Okay, should I say you you have told me about the principles of swarm intelligence, but while you're very correct, okay, your own your the principles you've highlighted are more specific to each individuals in the swarm. Okay, go back to that slide 6 again. So each individuals exhibits these behaviors and principles. Okay, so each individual agent in that swarm has awareness, is autonomous, solidarity, expandability, and resilience. Okay, but now that we're dealing with the entire swarm population, okay, there's something about the entire population that distinguishes it from each individual action. Because take away the system, separate the individuals. Okay, their behavior is more stochastic, unpredictable, unreliable, and just haphazard. But when they come together, okay, individually they exhibit these 6 principles that you have highlighted, but there are certain principles that guide their collective behavior. Okay, so one of them is homogeneity. That is, each agent in that system kind of exhibit homogeneous behaviors. No, don't correct that here. Okay, you have duplicated the slide. I don't want you to change.
Yes, I duplicated the slide.
Okay. So what you should say here is no, I don't think characteristics. I think you should call them behavior, principles of collective behavior. Yeah. So the first is homogeneity. That is, all the agents would exhibit the same behavior once they're in that system. Outside the system, the whole thing is just random. So without a leader, without someone guiding, although temporary leaders tend to appear, but without having someone championing the entire cause, they seem to follow, the same kind of track based on some of the steps you've highlighted in the algorithms, such as the pheromones trails, and the second will be velocity matching. That is, they are matching their speeds. So each agent tries to match the speed of the agent by its side. That one is matching the speed of the one by its side. And so you see that there's a uniformity in the velocity of motion in that system. Then you have locality. Okay, I think locality will be the fact that, from local. So each agent in that system is locally affected by the motion of the agent close to it. So unlike a global case where each one is trying to you know follow the global progression, each agent does not have access to the information about the global progression. It only knows what is happening by its side or around it. So locally, which means closing it down, narrowing it down to a specific part of that entire system. When we say global, it means the entire thing. When we say local, it means narrow it down to a certain region. So a an agent in a swarm would exhibit that locality so that its motion is kind of impacted by the agents around it. Okay, so its movements is usually determined or influenced by the agents that are around it. So, and there are a couple of things that the agent would use to identify, you know, identify how those around it are organized, so that it then adjusts its motion based on that. So it uses its vision and of course smell. That is for biological agents now. Okay, then when we now bring it down to maybe intelligent agents in AI systems, we'll be dealing with other factors or other things that are used. So of course it's going to be sensory components of the agents that will be used to determine this, including vision, computer vision. So another property will be collision avoidance, which means each of the agents would optimize their movements so as to avoid collision with nearby agents. So it's interesting to see how, when you look at ant colonies, you don't see collisions. Okay, there's a kind of there's this alignment, just like soldiers on parade grounds. When you see their movement, there's alignment. Of course, for soldiers on parade ground, it's more organized, because now we're higher intelligent beings. The whole thing is coordinated. There's training for that, and all that. But it's interesting to see how the whole thing still works with ant colonies. These guys, would ensure that they are not colliding with nearby agents. And then I think I've mentioned how many things already. 1, 2, 3, 4. What is not here? The last component will be centering, agent centering. That is attempting to stay close to nearby agents. So they kind of center themselves to stay close to other agents. Homogeneity would have an E after the N to make that correct. And I can see your PC is underlining behavior, which means this setting, your language setting is American. Okay, so in my case, I've reset the entire system to British so that you don't correct me when I write my British English. Anyway, moving on. So I just wanted you to, just want you to take note of that. That's very important. So let's now go to the algorithms. Let's dive into your various algorithms. I think I would like to start with, okay, let's start with ant colony optimization. Where are my questions? So when you talk about ant colony optimization, okay, let's start with what optimization is. What is optimization?
So optimization is should I use the word technique? Let me use the word technique. Technique or an action that is carried out to find the shortest or quickest solution to a particular problem.
Okay, and what then is optimal? You have talked about this, but I want to bring out a question from what you mentioned previously. So what is optimum, and what is an optimal value? Okay, what is an optimum? Let's start from there.
It's like this English class. Okay, so when we talk about optimum, so we're referring to the end point. So when we say we are taking an optimization technique. We're taking an optimization technique to find the optimum value of a particular item or a particular problem.
Okay.
So optimum refers to the end point or the value that is that or the goal that is taken through an optimization exercise.
Okay, because you mentioned that yes, your optimum is the resultant value of the optimization procedure. Okay, and it could be a minimum, or it could be a maximum, or it could just be, when you're not talking about maybe numerical values, it could just be the best. Okay, the best scenario, the best option. But you mentioned something that I just wanted to bring out. You said, I think either optimum or optimal. You said it's the quickest. How did you put it? The quickest approach to, or the solution obtained by from the quickest approach to solving or arriving at a problem. Something like that, isn't it?
Yes, sir.
Okay, so we are not really talking about quickest here because it really depends on the kind of problem. Some optimization problems, we're looking at the shortest paths. So the notion of quickest kind of makes sense here. For example, in a transportation problem, we're looking at the quickest paths. Okay, so the quickest pathways to arriving at the destination. In such a in such a notion, you'll be talking about the optimum being the quickest solution. Okay, but in the other cases where we're dealing with a scenario where we have values, okay, an option of values that are solutions to a particular problem, and we need to find out which of the solutions or which of the values, are the, or which particular value is the best in this situation. So which one is the best solution? You understand? Sometimes we're looking at minimum versus maximum. We're looking at a scenario of costs. We're looking at expenditure, for example. We want to find out of different expenditure options, you understand, or different expenditure values, which of these is the is going to be the minimum. We want minimum when it comes to expense or expenditure or cost. Then when we're looking at maybe profits and so many profit scenarios, we want to obtain the maximum. So when we're optimizing a profit scenario, the goal is to maximize. When we're optimizing a cost scenario, the goal is to minimize. So sometimes it's minimization, sometimes it's maximization, sometimes it's neither minimization or maximization per se. Sometimes it's just trying to get out the best possible solution. So sometimes it's quickest. Of course, it's hardly ever slowest, but sometimes it's quickest. But that's just one of the options. It doesn't necessarily mean every time you're looking for the quickest option. So I just want you to, I don't know if that makes sense.
It does, sir. It does, sir. So if I were to
Okay.
if I was to say something, sir. So in a situation whereby
Yeah.
we're building a system that should repulse or not repulse, let me use repulse. We are building a system that is supposed to mimic or imitate a real system so as to deviate or divert arbitral attack, let's say cyber attack or whatever attack that will be coming into that system. Wouldn't we be looking for the slowest path, like optimizing to the slowest path? I don't know if you understand what I mean.
If I'm getting it correctly, you have a system, a working system, but in order to divert or prevent cyber attacks to those systems, you kind of have a a kind of copy of that system, is it not? Where
Yes, sir. Yes, sir.
cyber attacks can be diverted to. Is that what you're saying?
Yes, sir. Yes, sir. Kind of. But then,
So,
when it's been diverted, the algorithm placed there based on swarm
yeah.
intelligence is to ensure that it it shows it outlines the longest path instead of the shortest path or the slowest path to get to. I don't know if I'm even making sense, sir. But it's just what
I'm
I
not really
think in my head, sir.
getting.
Maybe I'll just leave the question. It's just what I'll just even
No, 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 no.
I don't think I structurally put it together.
Don't start what you can finish. So we're going to treat this.
Okay, so what I was thinking actually was, so let's say you mentioned something that it rarely works for less for a slowest
Slowest.
system.
It's
So
always quickest, often.
yeah, so I was thinking, okay, let's say
Yeah.
I want to build a system that is
Okay.
resistant to cyber attack. But
Okay.
the way I built the system was, let's use First Bank system for example. I
Okay.
cloned First Bank system. I'm working for First Bank as a cybersecurity analyst, and I cloned First Bank system, and I duplicated the system as a layer on top of their real system. You understand me, sir? So
Okay.
the layer I duplicated on top of their
Okay.
real system was optimized so that when there's a cyber attack, it follows the slowest route to get to the main system. I don't know if that makes sense. And
Okay. That is the slowest route to the main system, not to the clone.
exactly, sir, to the
Not to
main
the clone.
system. Exactly, sir, to the main system. So the goal is
Okay.
to
Yes.
achieve the
Yes.
slowest route to the main system.
Then how about to the clone itself? Are you not trying to divert the attacks to that clone?
The clone is a decoy because the goal is, let's say if they are building a system, then they would have had the blueprint of First Bank and they know if they are pinging so that they are ensuring that it is the real system. So the essence is for the clone to take a fall for it as a decoy. But
Okay. But they will
the
still
goal of
eventually
the
reach the
clone,
main system.
but it's still the slowest part, so at least it can get detected.
Yes, in that case, it's true. The optimization process here will be the slowest pathway to arriving at that original system, and you want the algorithm to, of course, there'll be a selection here when such an attack is coming in. You want the algorithm to push the clone as what do you call it? As the receiver, the first receiver of that attack. Okay, then the original system kind of I don't know here because separate is my thing. So, but yeah, slow pathway is here. Can you
Yes,
hear
I
me
can
now?
hear you, sir. Yes, I can hear you, sir.
Okay, so let's move on. Let's start with this ant colony optimization that you talked about. So, of course, when we're building optimization models or optimization algorithms in swarm intelligence, what are we trying to optimize exactly?
If we're using ant colony optimization, then we are optimizing the distance. We are looking for the shortest
Okay,
path to.
let me put that properly. We have the evolutionary algorithms that Precious handled, and the optimization we're looking at, okay, was more individual specific. Okay, we are optimizing not the entire system, but we are trying to optimize a uh, um, specific individuals or properties of specific individuals. So we are running the optimization algorithms on specific individuals in the entire population. Is that the case for swarm intelligence, or is there a different scenario? Is the
So for
optimization technique a different one?
so for swarm intelligence, the optimization technique is different for ant colony and particle swarm optimization. For ant colony, it is the optimization technique is for the whole team, for the whole group, for the whole system entirely.
Yeah.
While for particle sum optimization, the optimization is for the agents, individual agents in the swarm or in the group.
I'm going to disagree with that. Um,
Okay.
they both are global optimization algorithms, which means we're optimizing the entire system. Although the goals may be different because you may be looking for particle swarm optimization, you may be initializing, yes, you're initializing the system with random candidate solutions, and then probably you're iterative each of the agents. But in ant calling optimization, so like I was saying, they are both global optimization algorithms. You get so evolutionary algorithms. The optimization you're dealing with there is kind of local optimization. Okay, you're narrowing it down to each specific member of the population, individually treating them. You know, Precious talked about fitness functions and all that. Not really competing, unlike evolutionary algorithms where you're computing fitness functions for each of the agents, we're not really computing any such function for each agent. We are treating the entire system as a whole because, just like I mentioned, the principles of collective behavior. Okay, the goal here is to optimize the collective behavior of the entire system. Does that make sense?
Yes, sir. But if I may ask, for particle
Okay.
sum optimization, where first before each agent optimizes the G best, which is the group's best fit function,
Okay.
each agent optimizes its own fitness function based on the closest neighbor, which is optimizing its own P best. Wouldn't that be considered as optimization, agent optimization before global optimization?
No, 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 no. How do I put that? That is part of the global optimization. Okay. Okay. Tell me what is a P best? What
The
really
P
is a
best
P best?
is the fitness function of the velocity of a particular agent against the closest neighbor.
And how does it arrive at the value of the P best of that fitness function?
By analyzing its own velocity relative to its environment of the particular space.
Okay. Now we are not dealing with optimization here, having I saying? What was I
Yeah,
saying?
we are trying to explain.
The, yes, I remember. We will not call those the computations of those fitness functions. We will not call them optimization per se. Thing here is that it computes the fitness function and then it tries to update it. It tries to update based on the value it has. Tries to update its velocity based on the velocity of nearby agents. Am I correct? Is that what it does?
Yes, sir, that's what it does.
Okay. Now we are not having a computation where you have different solutions of the fitness functions and trying to get the optimal solution to a set of solutions, a set of solution options, then trying to get the optimal solution, which means for you to arrive at each solution, it considers if iterations or variations of so many possibilities for computing that fitness function, to look at so many different possibilities, each one having its own solution, and then try to optimize to pick out the suitable fitness value for that. Unlike in the evolutionary algorithm, we're computing the fitness function, we're evaluating the system itself, I mean the agent itself, and considering, so many scenarios, and then uh, um, picking out an optimal value from there. So this process now, it's not like the entire algorithm is system based, not individual based. Because in evolutionary algorithms, you have an individual based um, optimization algorithm where you are trying to see whether you want to eliminate a particular member. So you have to completely analyze that member. You keep running the steps. If one member is fit, for the next step, it moves on. Otherwise, you terminate. So the loop or the before you get to the termination loop, you're actually working with each member in the population. You're looking at each member in the population, taking it step by step. Of course, you're starting with a representation of the population. Then you begin to now look at each member. So you're optimizing for each member in the population. But here you're optimizing for the entire population because the goal here is to make adjustments suitable for the entire population. If you're trying to optimize each member in the population, okay, then the goal, of course, you'd have some problems because some members would end up having either more speed than others, or they will end up colliding with others because solutions we get for each member will be different. So they will end up, being completely, each one would then just detach from the system because they would have certain properties that others might not have. What you're trying to do here is to enable them, uh, uh, um, enable them consist of or enable them exhibit similar behaviors. Okay, so you're not trying to optimize to make one have better behaviors than others. You're optimizing the entire system for each individual member to have similar behaviors, not like optimizing each of the systems. So, it can be confusing when you're talking about you're computing certain things or properties of each of the agents and updating values for each of those to match the others. So it's like you're optimizing, but you're not really optimizing for that particular agent. You're only updating, and so that updating process is part of the general optimization. I don't know if that makes sense.
Yes, it does, sir. It does.
I mean, if you still think otherwise, I'm not here to say this is
No,
how
no, no,
it
no.
is.
No.
I want us to, yes, my approach is really, even when I know I'm right, okay, I want us to walk through the whole thing to arrive at a solution where we both know that, okay, this is, what it should be. You get?
Yes, I agree, sir. I just needed to understand the
Okay.
cloud and clear the cloud. Yes.
All right. Now, let's focus now on ant coding optimization. So yeah, you talked about you said some things here that's you didn't really explain, like NP hard problems. Yeah, I know you're talking about applications, but when we say NP hard problems, what do we really mean by NP hard problems? Okay, that is non-deterministic polynomial time problems. So in computer science, we have P problems and we have NP problems. And in fact, there's a particular Millennium Prize problem in mathematics today that if anyone solves, you get $1 million. So there are 7 millennial problems in mathematics. That is probably millennium problems. We're talking about problems that were identified from the beginning of the 20th century up until now. Applications, they will have serious implications not just for mathematics but for so many other branches of science, including computer science and even engineering and technology. There's one for fluid mechanics. Okay, I think it's the Navier-Stokes equation. We use the Navier-Stokes equation in physics, but the truth is that it's a mathematical theory, and there's no solid proof for that theory. So even though it works for physicists, mathematicians are concerned about getting a proof of the various theorems and conjectures in a theory to ensure that we really have a valid equation. You get. So that's one of the millennial problems. So there are 7. Then apart from that Navier-Stokes equation, we have the P versus NP problem, which is dealing with polynomial time and non-deterministic polynomial time. So what do you really mean when you say polynomial time and non-deterministic polynomial time for people like us that are finding it complex to understand? Because you have to ensure that we understand the terminologies that you use in the problem.
Okay, sir. So when I say NP problem, I'm
Okay.
referring to solutions uh, that are hard to find but can easily be solved. Should I use easily? Okay, let me say can be solved by using non-deterministic techniques.
What do you mean by non-deterministic?
So I try to explain that this I think at that section of my slide when I say deterministic
Okay.
technique and non-deterministic technique. So I'll use a contrast between the both of them to try to pass an answer for the question. So when we say deterministic technique, we're saying that a technique to solve a problem where x number of input will always give a static output at any given time. And non-deterministic is when that same x number of input will give varying output at
Yes.
any given time.
Okay. So when we now talk of polynomial time, what is a polynomial time?
So that one I did space small. I would
So
appreciate your breakdown.
you see, there are some solutions that when we're trying to solve, we talk about computational time, but that's coming to computer terminology now. But mathematically, we also talk about polynomial time. So there's you can't solve with the allocated time for that problem, or should I say, the computational complexity of that problem is such. You know what? Um, Let me just try to instead um, use a what's it called? I would, so I would Google it. I'm going to override your screen now. I would instead Google and explain from there so that it's a lot easier for me to give the explanation. It's a tricky terminology. So what are we talking about here? Polynomial time. So um, I hope you can see my screen. Why is
Yes,
this
I
stuck
can.
there?
I'm seeing it.
So from the definition here, we see that polynomial time is the time required for a computer to solve a problem, where this time is a simple polynomial function of the size of the inputs. So I want to here, let's deconstruct what is here. Let me increase this. So when we're talking about polynomial time, we're talking about the time required to solve a problem. Okay, so the time it takes a computational process to be completely executed. Now, this time to solve this problem depends on the size of the inputs. So we express time as a function, a polynomial function of the size of the inputs. So where input increases, okay, because you're talking about a polynomial here, what does that mean? Which means you are going to be having here, an independent variable will be having powers. Okay, you would have powers in that equation, and so if the inputs increases, okay, the time increases by the scale of that power for the independent variable. I don't know if that makes sense. So you're talking about, you know, how time would scale as the size of the input increases. The scale of the time would scale according to the power of that. For example, if you have x squared, if you have t as a function of x, just x, as x increases, t increases. So if x increases by 1000, t would also increase maybe by just around that same scale. But you add a power to x, so let's say you have x squared. As x increases, t would increase rapidly by that power scale. If you increase x even more, t increases even more. If you increase the power of x, then as x increases polynomial time. And then when you're talking about non-deterministic polynomial time, I think we should also Google that. Here you would also be dealing with cases where you're not going to have a specific solution of the time function. So here you have the set of decision problems solvable in polynomial time by a non-deterministic Turing machine. Very good. I wanted to bring in this notion of a Turing machine. So in AI, we have NP hard problems. That is, problems that cannot be solved in computational time. And these problems were kind of, are kind of related to the notion of a Turing machine. So, oh my God, there's so much to unpack here. So let's just run a search for this so that you know what a Turing machine is. So a Turing machine is a mathematical model of computation that defines an abstract machine that manipulates symbols on a strip of tape according to a table of blah, blah, blah. So basically, from the AI notion, a Turing machine is simply a computational model, or it is written a mathematical model of a computation. But that computational model, kind of defines procedures for running algorithms. So when you come back to a NP problem, you're talking about now a problem that cannot be, a set of decision problems that is solvable in polynomial time by such a machine, but this machine is non-deterministic, which means we are not going to be having, we're kind of having a stochastic outcome here. Okay, so when you say non-deterministic, it's more like stochastic. Deterministic means we're expecting a single outcome. Non-deterministic means we're expecting random outcomes. And so when we say NP problems, we're talking about three things here. Number one, we are talking about a set of decision problems. So which means we're looking for an optimal solution or an optimal decision option. We're talking about the optimization being carried out in polynomial time, where polynomial time is a time function that kind of maps the set of inputs to, or maps the time to the set of inputs. And then we're talking about a non-deterministic Turing machine. Now, when we say an NP-hard problem, we're talking about problems that are very difficult to solve by this Turing machine in polynomial time. I don't know if that makes sense.
Yes, I do.
So when we say a problem is NP-hard, you can represent your screen again, Samuel. We're simply saying that this problem is very hard to solve by Turing machine, a non-deterministic Turing machine, in polynomial time. Why? Because of the time complexity. Okay, so now the time function will be such that we have high powers in the function, and therefore as the problem scales or as the input scales, time scales even higher. Of of then coming to AI now, examples of NP hard problems, or all the NP hard problems are usually called AI hard problems. Like natural language processing is an AI hard problem, because if a computer tries to solve a natural language process, tries to process natural language, it can't complete the process in polynomial time. Okay, it's very hard for computers to solve natural language problems, which is why we need to now build AI solutions to enable computers process language, you see. So you just need to be able to clarify some of the terminologies you used. That's very important. So I think I will just move on straight to, because of time, let me move to particle swarm optimization. Or let me see what you have in that pseudocode for, that flowchart for ACO. Now, let me mention, let's try to narrow this down to, or should I go to PSO first before we talk about narrowing down? Let's go to particle swarm optimization. If I talk about narrowing it down, everything you're talking about to AI systems. So you talked about PSO being a population-based stochastic optimization technique. I think I'm tempted to ask you what is stochastic optimization, but I think part of what I've talked about is like covering. But let me still ask you, what do you mean by stochastic optimization? What really is stochastic optimization? I hope you can hear me. We already talked about what optimization is. So when we now talk about stochastic, what then do we mean when we say stochastic optimization? Quite tricky. But once you are able to reconstruct that, then the rest is easy.
Hello. Can you hear me?
I can't hear you clearly.
Can you hear me?
Yes, I can hear you now.
Okay, so shallowly, I think it's a stochastic optimization technique is a methodology that is used to find the minimum or maximum function that can be used to solve a problem that involves randomness. I think that's what I think.
Okay. Yeah, a problem that involves randomness here. So in a stochastic optimization procedure, we'll be talking about initializing random candidate solutions. Okay, so we're dealing with random outcomes or random solutions, and we're trying to optimize to find out, the the optimal solution or action or decision for for that set of various options. We're talking about randomly occurring options, or we're talking about random outcomes or random events. So that's why we say stochastic. And of course, stochastic is like the opposite of deterministic. True or false?
True, sir. True.
So the stochastic is the opposite of deterministic. So a normal optimization technique is a deterministic procedure, but when randomness is involved, then it's stochastic because the outcome or the iterations are not exactly following a specific process or a specific method, or the outcome is not specifically defined or outlined. We're looking at something that has a notion of randomness in it. So that's very important. All right, thank you very much for that. That was a good one. So let's move on to the algorithm for. Did you outline the algorithm for PSO?
Sorry, I don't think I
What's the next slide?
The next slide is assumptions and then analogy and then
Okay. Let me move. Let me see the before that flowchart. Let me see what you have on that slide.
what I have is the assumption.
Before the flowchart. Okay.
Yeah,
Suppose the following scenario. Okay. So I want to see how we can now narrow this whole thing down to an AI system. Okay, so that's more or less what I really want to achieve here. How can we now narrow this down to an AI system? So let's start with ant colonies. Um,
okay, like
every time I talk,
is it like an application? Do you mean like an application, sir? A real life application of ant colony?
we don't necessarily need to. Why am I hearing these echoes? Hello.
I can hear you, sir. I can hear you.
Okay, I was hearing some echoes. All right. So not necessarily, we don't necessarily need to specifically consider a an application, but we just need to understand the principles of the constructing it in terms of AI. You get. So let's now from ACOs, from the concept of ant colonies. Okay, let's now think of this. You have two areas, at least two areas in AI, where it is most feasible to apply swarm intelligence. And what are those? You mentioned one already. What is the you mentioned one specific field of AI where swarm intelligence can be applied.
And
And then I'll talk about the other one.
that's swarm robotics.
You said what?
Swarm robotics, sir.
Yes. So in the field of intelligent robotics, we can apply swarm intelligence. And so what we'll be doing here is that we want to build a system of intelligent robots, and we want to see some collective behavior. We want to build a self-organized robotic system, more or less. It's a self-organized system of intelligent robots. And that's the goal when we are trying to apply swarm intelligence to that field. The other area is multi-agent systems. Okay, so we have intelligent agents, but we also have multi-agent systems. And in multi-agent systems, we're simply looking at interaction of several agents in a particular system. And these interactions, they can be different types of interactions. But when we're looking at applying swarm intelligence there, then we'll be considering not just interactions, but highly coordinated interactions that lead to self-organization, so that collectively as a whole, the multi-agent system can take decisions, can carry out actions collectively, and can exhibit, you know, can exhibit coordinated decision-making processes using the principles of collective behavior in swarms. So that's like those are like the two areas. So if we consider any of these areas like multi-agent systems or intelligent robots, a system of robots, we can then see how to narrow down the whole thing. You understand? So let's now look at the ACO algorithm. Okay, let's start with ant colonies organization and try to see how we can narrow down the whole thing to multi-agent systems. Can you show me
Okay, sir.
the flowchart for ACO so that we just speak from there? Before the ACO, did you define um, certain requirements for designing the algorithm? Let me see your previous slide.
No, I didn't. I didn't do that. I only just gave it your
Okay.
biological theory.
Okay. I like the explanation here and the theory for ACO. You gave comprehensive details about the various things considered, and I like that you were looping back and forth between this slide and the flowchart to illustrate what we have in this diagram, because at first glance this diagram can be confusing. So we need to be able to really understand what is going on here from the perspective of from the algorithmic perspective for ant colonies optimization. So let's go to the flowchart. Let's look at um, yeah. So we are starting. So when we start, what's the first step here? What's the first thing we consider?
To
What's the first step
initialize
in the algorithm?
the iteration count, and then to set the shortest length, and then also initialize the best solution for the shortest length.
Okay, so of course iteration counts. Um, of course it starts from zero. Shortest length starts from zero. Best solution for now is zero, but we're
Yes,
going
sir.
to be looping back and forth
Yes, sir.
to do some adjustments. Okay,
Yes, sir.
so which means in these initialization steps, okay, you would also be talking about initializing the pheromone trail, okay, the trail of the pheromones. You're initializing that also. Then the next steps, you then begin to construct solutions. Let me see. After the initiate ants, each ant finds a route according to Formula One. Where is the Formula One?
So if Formula One is based on initializing the count zero, so one of the counts
Okay,
are initialized that's based on Formula One, which is here.
okay. So is this where each ant computes a solution? Yeah, I think that's where the solution is constructed.
Yes, sir.
So more or less like this first box here and this second box, these are like the um, initialization. So both of them fall under procedure one in the algorithm, which is initialization, where you'd also be initializing the pheromone trail. And then after this, you have this is more like this second. You know what? I'm actually pointing on this screen as though this was my slide. I'm forgetting you guys will not see it. Put this on slideshow so that it gets bigger.
Okay, sir.
So on the fourth box here, the first box is starts. So the fourth box, where each ant finds a route, this is the step for solution construction. And this solution construction, what is used to construct the solution? How does each ant construct a solution or find a route? What is the one thing that is needed here?
Please come again, sir. I didn't hear you, sir.
I don't know if that
Please come
question makes
again.
sense.
I didn't get you. Please come again, please.
Okay, we are talking about the solution construction in this step.
Yes, sir.
Or you mentioned each ant finds a route. So what
Yes,
does
sir.
in the solution construction, what does each ant need to construct the solution? What do they use to
Distance.
find these routes? Yes.
Distance. They use distance, sir.
And how did they get the distance? How did they arrive at the distance?
They compute the difference. They compute the distance from the origin to the source from
And
their
to compute
particular
that
position.
distance, what do they need to sense, to compute the distance? I don't know if the question makes sense.
I'm trying to grab my I'm lost. I'm lost when you say what they need to sense, sir.
Okay. We are talking about pheromones here, is it not?
Yes, sir.
The ants leave a trail of
Yes,
pheromones.
sir.
Yes. So they need the
Yes, sir.
pheromones to construct their solutions. So each ant will
Yes,
construct
sir.
a complete solution to the problem according to, we are looking at, there's a notion of randomness here. So there are some probabilistic rules that will apply here. But basically, they will be using the pheromone trail. So I just want to walk through this algorithm, then we'll see how we can relate the steps. So step one, these two boxes here, initialization of the pheromone trail. You're initializing the pheromone trail more or less, because by the time you start iteration count from 0, you start shortest length. You are basically initializing the uh, uh, pheromone trail. Okay, so each ant is analyzing the the, the, uh, the pheromone trail. So we start from ground zero at the beginning. Then second step, solution construction. Each ant will determine the route. That is, each ant is constructing a solution based on the pheromone trail.
Yes, sir.
Does that
Makes
make
sense.
sense? Okay. Then finding the shortest route, construction. Okay, because we are you are initializing. I mean, not initializing. You are computing a solution of the routes based on the pheromone trail, but you will likely have or see so many routes. So finding the shortest route, and this more or less where optimization comes in, because now you are going to find all the ants should be able to arrive at the same result for the shortest route. True or false?
True. True, sir.
Okay. So I use routes and I use routes simultaneously. Both ways is correct. So in case anybody is wondering, so uh, uh, um, when each ant computes, the solution, or construct the solution of the pheromone trail, they should all arrive at, an equivalent value for the shortest route. Of course, there will be slight differences, which is why the movement will be slightly different. The uniformity will not be exactly 100%. There'll be some probabilistic differences. Does that make sense?
That makes sense, sir. Yes, sir.
Yeah, which is why sometimes you see they're not moving like soldiers on parade grounds where there's 100% alignment. There's still going to be differences, but at least the value for the shortest route should fall within an acceptable range. Okay, so that the margin of error between each solutions would be very slight. Then,
Makes sense, sir. Makes sense.
so these first two boxes, initialization. The second two here, moving from this second one, each and finding a route and finding the shortest route. Both of them fall under solution construction using the pheromone trail. And then the third step will then be um, the pheromone trail updates, which is this you've highlighted here, updating. Now that they have found the shortest route, they now need to update, the values that they have computed. And so all these quantities will be updated. So basically, you're going to be having, that's why it's the global optimization. You're not optimizing for each individual. Each individual are working to calculate or to compute global values. So the entire system is, all the agents in the system are working together, more or less. Yes, there's autonomous computations for each of them, but at the end of the day, they are arriving at a global optimum. Does that make sense? Are you with me?
Yes, it does. Yes,
Remember,
it does.
remember that when I talked about global optimization, I'm saying when you're looking at the entire system at a glance, local optimization is now zooming into the system to fish out a specific member to carry out optimization techniques. The optimization technique here is global because we are looking at optimizing the entire system to complete this, to compute a single, value for the pheromone trail, and then uh, um, a global rule will be applied for each of the ants to update, the values, these values. Do you get?
Yes.
So there's a global updating that will go on here. All the ants would update according to the computations. Why? Because we want to ensure that the entire system is getting a uniform value, not each individual doing what they want. At the end of the day, there will be no coordination, there will be no exhibition of collective behavior. This topic and precious topic, they are really interesting. And I really loved your presentation and precious presentation. This is like a session I've enjoyed the most compared to previous sessions. I mean, others did well in previous sessions, but this one, I think I really enjoyed it. I really did. Okay, so after this step, so step one, after your start is like step zero, of course. Then step one, initialize. Step two, construct solutions. Step three is what?
Update solutions
Yes, update. And what is the solution?
to the shortest
The
path.
solution we're dealing with here, what quantity is represents the solution?
Distance.
Yes, the pheromone trail. Okay, the pathway. The pathway is what we're talking about. And in the pathway, there's so many
Sorry,
values
can
we
I ask
look
a
at.
question, sir?
Yes.
So how would you relate to, biologically we can look at it as a pheromone trail, but that's where I've been
Yes.
trying to make an interlocking. Biologically we can say, okay, ants pheromone trail. So mathematically, or let's say
Yes.
scientifically, how would you represent a pheromone trail? Let's say we are
You know,
expressing the function mathematically. How
okay.
would we abstractly represent a pheromone trail? We can easily
Yes, that's what.
reference distance and say distance is origin zero minus
Mm-hmm.
current position, or target origin minus current position. We can always compute the distance from there. But then how would you compute pheromone trail
Okay.
and say, okay, we are transmitting pheromone trail from A to sense, B to sense, C to sense?
That is, you are talking about the pathway, right? Not just the
Yes,
distance.
sir. Yes, sir. Not
Yes,
just the
I'll
distance.
get
Yes, sir.
there. That's actually my destination, but I want us to go over all these steps first of all. I want us to go over each steps in the transition not just transition in the algorithm. I want us to go over this, and then what do you call it? We uh, we then translate those notions back to, or coming home to, the mathematical sense and the AI sense, of course. So, if I was preparing this slide, I would have actually added some equations. You would see some probabilistic models here. Because, of course, probabilistic modeling is very important for this. Now, the third step, we are updating um, the uh, um, the pathway, the pheromone trail, and in doing that, some values will be updated, like the shortest length that there should be between the various agents. In this case of ants, the shortest length between the ants. Why do you think there should be a shortest length between the ants?
To achieve the swarm's goal, since they are all
Not
independent.
really. There should be a minimum distance between the ants to avoid collision. Okay, sorry. This shortest length is not just the distance between each of the ants. It's talking about the shortest pathway. Sorry, I was misplacing that. So the shortest pathway is what we're talking about here. Okay, so given so many options or so many solutions of the pheromone trail, the shortest path to arrive at the destination. So sorry about that. Okay. But of course, we want to ensure that there's a minimum distance between the ants so that there's no collision. Then after this step, um, then increment iteration, and then of course you're going to loop over again. As the movement is taking place now, it will continue to steps until you get to the destination. So when it gets here, it checks, have we reached our destination? That's when it gets to this stop sign here. Have we reached our destination? No. Initialize, repeat the loop until we get to the destination, then we stop. So coming to the AI sense, how do we now, um, how do we translate this now to a computer system, starting from initialization? Okay, so we have, now we're not talking about just any type of AI model. We're talking about multi-agent systems, okay, or intelligent robots, which means very likely we'll be having systems that have actuators. When I mean actuators, they have components that enable them to carry out actions. So they have sensors to receive sensory inputs, perceptory inputs. Then they have actuators to carry out actions. Some of the actuators will be embedded in physical hardware. In the case of intelligent robots, you would have actuators that will be embedded in the legs of the robots or in various movable parts of the robots to act on the environment. So we'll likely be working with agents that are implemented in hardware so that you can have these movements. I don't know if that makes sense.
Yes, it does. It does.
So that when you're doing swarm intelligence now, applying swarm intelligence to these systems, you can now physical hardware systems where you have an internal software that is carrying out these various an internal software or internal softwares that are actually these individual systems, individual agents, okay, and then each of the individual agents are implemented in hardware or embedded into hardware system, and so you're looking at the system of several hardwares. But at the end of the day, those hardware systems, you know, uh, uh, um, they make up the swarm. But each time you look at the hardware, you are really looking at the intelligent agent or the software that is powering what the hardware is doing. Does that make sense?
It does, sir. It does.
Yes. So given a goal you're trying to achieve, okay, you have a system of these robotic agents. Okay, so you want to carry out ant colonies optimization on these robotic agents. So they have where they're headed or where they're going, and individually they will not be able to arrive at the goal that you want. We all know how stupid current robots are. So current implementations of intelligent robots are still really terrible, you know. So speaking of the application of swarm intelligence now, we can enhance these behaviors by bringing or um, by putting them together in a system and implementing these optimization steps to coordinate their behavior so that you can have a more coordinated behavior. Then from here, we then begin to run those steps. We start from pheromone trail initialization, but here you're not going to be dealing with pheromones. I don't know if that makes sense. So what are we going to be talking about here? We want to narrow it down. Okay, so I want you to answer the question now. I want you to answer this. I want you to think about it. What are you going to be dealing with here when you're talking about pheromones in ant colonies. Now you have, should I call it robotic colonies or multi-agent colonies? Okay, you have such colonies, and now um, you are bringing so many of the agents together. Then you instead of a so as I was saying, where did I stop? Instead of a pheromone trail that kind of leads to the destination, okay, a pheromone pathway, okay, what do you think we're going to be having in the case of a robotic colony?
All right. So, in the robotic colony where we have swarm intelligent robots, I believe the pheromone trail will be signals that they'll be communicating among. Hello. Hello.
Yeah, I can hear you. Sorry, my power went out again, so I would have to turn on the gen so that we don't. Just give me a second. While I'm doing that, still continue thinking about the question. If you talk about a signal, let me just quickly respond to that. Your response. If you talk about a signal, is a signal really a pathway? A signal is like the pheromones. Okay, um, you can call that signals, and so just like the ants would have sense of smell, the agents have sensory or perceptory. They have sensors for perceptory inputs where they can capture these signals. Okay, but what would the pathway be itself? We have the pheromone, we have the pheromone trail. So what would be when we have signals? What do you think would be the trail? So I'll be back. Have you been able to figure it out?
So I think if I was to draw correlation from
Yeah.
ants and the pheromone trail, I would say that the pheromone trail will be signal strength.
Okay. The pheromone
That's what I
trail
think.
will be signal strength.
For yes, because if ants are updating their shortest path based on the strongest pheromone scent, which likely would evaporate less, then I would say that the robots will be updating their position based on the strength of the signal. That's for the shortest path.
Well, I think the strength of the signal will probably be one of the solutions or one of the values that you'll be considering to update. That is, each agent will be considering to update, but not necessarily the entire pathway. Let's say they might have a destination. Okay, they might have a certain destination. It really depends on how we're looking at it. It could be a transportation problem where they are moving to a certain destination, but could also be a goal-based problem where they're trying to do something or get something done. But let's to make it more relatable, let's consider a transportation problem. Do you get? So the transportation problem would just be a maybe a value chain, you understand, or a supply chain, depending on what you're dealing with. You understand? So it's the pathway we'll be dealing with here will just be a a, a pathway with the notion of physical distance. Okay, so a physical pathway is what we're looking at here. Does that make sense? But the pathway from the notion of a pheromone, I think I would agree with you. Yeah, I would agree with you. It will be signal based. It will be signal based, but not necessarily the signal itself, but like a signal based progression, a signal based trail. Does that make sense?
I think it does that.
What I'm trying to achieve here is for us to walk through the process for applying this now in AI, so that we're not just dealing with ants, we're now looking at how it can be implemented in a real world AI system.
Very true, sir.
Yeah. So the next step, of course, in the initialization step, the initialization step, which is what we're talking about here, we're trying to initialize the distance. So everything starts from 0. Your iteration count 0, shortest length or shortest distance is 0, the best solution is 0. So we initialize the let's call it a signal trail. Okay, we initialize the signal trail. Then step 2, which is these two boxes, the next two boxes in your slide. I mean the first two boxes in your slide after your start belong to step 1. Then the next box here would belong to step 2. So the third box here and the fourth box here are under step 2, which is the solution construction. So after the initialization, they begin to construct solutions for the, what are they constructing here? What solution are they constructing here?
Relative to the swarm robots.
Yes, for the robotic agents.
They'll be constructing the shortest distance to the target location they are heading to.
You have used a very long sentence for that. So
Okay.
just give me 2 words.
They are constructing a pheromone trail.
Not pheromone trail now. Let's use signal trail.
Signal trail. Okay, signal trail, sir.
Yes, so they are constructing this solution for the signal trail, or they are constructing the optimal solution. So trying to find what the optimal route is to arrive at their destination. So in this case, the optimal route is the shortest route. And so that's step 2. Then after step 3, okay, still under this step 2, before the updates, okay, they would also compute, one of the things they'll compute here, or they'll try to optimize is the transition. Okay, the transition to that destination. They already computed the routes, but they also need to compute the transition. So they would need to compute their movements. You know, if you've seen some really intelligent movies on robotics or intelligent systems, I'm not talking of terribly exaggerated AI systems. I mean AI movies or sci-fi, all this sci-fi exaggerated stuff. If you've seen some of those really really relatable ones, you notice that some of these agents, okay, when they want to move a particular distance or want to go to a particular destination, they carry out some computations. Okay, a very practical example is this movie, Resident Evil. Can you remember Resident Evil?
Yes, I remember it.
Yeah, Resident Evil. Let's talk about maybe one of the, I think the last one was Retribution. So was it a trilogy? I think it was a
The
trilogy.
movie is more than a trilogy. The movie has several variants, a lot of variants on Resident Evil.
Okay, so let me just talk about maybe Resident Evil Retribution. So towards the end, I can't remember the names of the characters again. You know, but there was going to be a fight between this girl and um, whoever the girl was. And so before the fight started, the guy had to do some computations. Of course, is a machine, is a computer system. So he's an agent. So he did some computation. Of course, the girl is also had become kind of an enhanced agent, like um, robotically enhanced human. So she could also do run some computational algorithms. So this guy did the computations and already told her that she won't be able to reach where she could pick the penknife to attack him. and gave the steps why she would not be able to achieve what she initially intended to do, because she ran the computations to try to fight him. She ran a simulation for what she would do to arrive at a goal. And the guy also ran a counter solution, a counter simulation, to tell her why she would be defeated. Why? Because the very first step in her iteration was to reach the pen knife, but she will not be able to reach that pen knife, and so she'll be defeated because she didn't make it to the pen knife fast enough. He was able to then attack her. That was his own simulation. Now, in such a scenario, okay, you're not just looking at maybe trying to find the optimal pathway for doing something. You'll also be looking at transition, which means your sequence of movements to actually arrive at that destination. You've calculated the pathway. Okay, what is the sequence of movements to arrive at the destination? I don't know if that makes sense.
It does, sir. It does.
Okay,
It does.
so I hope this is not getting boring.
Not at all. There are a
So
lot of expositions that you are giving, especially with relativity to real life scenario for robotics itself, and how they can relate to yourself. Because while researching on this, I kept trying to relate it and say, okay, and that's where I stumbled upon that video. How does
yeah,
swarm intelligence relate to real life? Let's say I'm
really
building
work.
an intelligent
Yeah,
system, and that's where I found the use of starting lectures where you taught us intelligent systems and intelligent agents, and so I began to see relativity in terms of intelligent agents within a swarm intelligent system. But then I kept on looking, okay, what would be the mathematical correlation of pheromone trail, birds as an example? How would find practical correlation to real life in terms of drawing up a mathematical function as an abstract term while trying to design such an elaborate system as a swarm intelligence system? So I'm really enjoying the conversation because beyond just enlightenment, it's also filling up a lot of loopholes in my head.
yeah. So the whole concept here, is very practical. If you're looking at it just from the exact presentation of analytical learning optimization, it looks like it's just so abstract and theoretical, but it's actually highly practical. And trust me, this is not something that we just have in theory. This is being, there are systems that are being developed around this. Of course, there's a lot of, baby steps and early innovations in all this, but, into this to build actual systems, to realize actual systems that can carry out this self-organized behavior, or that can show self-organized behavioral patterns. So step one, we've talked about the initialization. Then step two, I've talked about the solution construction. I think part of the solution construction would be the state transition I just talked about. The transition, itself, not just, in fact, I can put the transition as step four. As step three. So that in your diagram here, after the shortest route, before you talk about updating, you should talk about transition, because you will not really consider computation of the transition as part of the solution for the signal trail. You want to separate it because you have the signal trail, you have the shortest signal trail, you have the solution for that, the solution for the transition. What is the optimal transition? Now it will have to optimize the transition for each of the agents. So a general transition rule, remember, is a global optimization problem, which
Yes, sir.
means a general transition rule needs to apply to all the agents so that they kind of follow it, so that there's an organization in their transition, not each one having his own transition solutions, and that could lead to collisions and could lead to a lot of disparities in their movement. Does that make sense?
Yes, it does, sir. It does.
Okay. Um, so after this, we now update. Of course, the idea of update here is already easy. we already know that the pheromone trail in AI, we're talking about a signal trail. That's in a robotic colony. We're talking about a signal trail. For the pheromone, I mean, yeah. Then the next thing we're talking about distance, or not distance now, movement transition. So we carry out the updates with shortest path, best solutions for the transitions, and a couple of other things. Then we go to the next step of iteration, and carry out all these loops again. Of course, when you're computing, some of the steps, especially trying to compute, trying to carry out the solution construction, you will need to run some sophisticated models. There's some equations that will apply, of course, depending on the kind of problem, but most of the equations will be probabilistic, especially in the case of particle swarm optimization. Talking about a stochastic optimization technique, then you know that you're going to be using a lot of heavy probabilistic models to compute, all these various steps. And there are interesting algorithms for these interesting algorithms, including for loops and while loops to achieve your iterations. For example, here, this part where you get to before stop, this stop, what you really have here is a while loop, is it not? If you take a look at this, I'm doing the movement on my screen here. You will not see what I'm doing. So can you put your mouse over stop? Are you there?
I've done that, sir. It's over stop.
I can't see
But it will
that.
disappear over time. The mouse will disappear over time. The mouse will disappear over time because it's a slideshow.
Oh, but when you move it, does it not show?
When I move it, is it? I'm moving it, sir.
See anything? No. Okay, maybe come out of the slideshow. Let's see. Okay, I can see the mouse now. Now let's go to your so there. Now that looks like a while loop. Okay, because it's checking, have we gotten to a destination? Not a destination. Repeat. Is it not?
Yes.
Can
Sir.
you hear me?
Yes, I can hear you, sir.
Okay, I want you to tell me, okay, for loop you're using here or a while loop?
It's a for loop.
Why is it a for loop?
Because for each count on the iteration, for each orbit on the iteration, it keeps going until a particular condition is met, which is the shortest route. It keeps getting updated, and then after that, so for each update from each of the each of the agents, that's why I say for loop. It's updating with a condition from each of the agents.
I kind of disagree. You know why I disagree? I'm talking about incrementing here. So your while loop starts after this initialization. Okay. While the end criterion is not met, carry out all these other steps. When you get to this second to the last before stop, increment the iteration. So I equals I plus 1, or maybe t equals t plus 1, depending. Increment. Then check, is the while loop condition true or false? Is the Boolean condition true or false? So what is the Boolean condition? Criterion is not met. Does that make sense? The end criterion is not met. So while the end criterion is not met, run that loop again. So if it checks the end criterion is not met, true, it will run the loop until the end criterion, that condition returns false before it's before it stops. I don't know if that makes sense.
It does, okay, it
Yes, go
does, sir.
ahead.
It does. I on the second thought, it does. It does, sir.
Okay, no, I want you to, I still want you to express your distance so that we look at it. I don't have to always be right.
No, no. The idea is that I'm coming from, let me say, a less informed point of view. So I would, in as much as I have my own position, I would always want to take a more better cognitive reasoning regarding the subject matter. So when you give an analysis, I first sit back, consume it, and then refer it on the current case scenario, and then I'll look at the difference. And then yeah, that's why I must tend to agree.
Okay, all right, no problem. So we've spent a lot of time already. 2 hours of precious, 2 hours for you. Interesting. So I think we should just really stop. Um, we should just stop here. What's the time now? Wow. So we've already looked at a couple of things, and hopefully we've been able to arrive at the applications for tomorrow. I say for tomorrow. Sorry, a message just came here where tomorrow showed up. So that entered what I was trying to say. So we've looked at the applications, narrowing it down to an AI system, and you've actually done well answering some of the questions. So we can stop here for now. Would be I'll be taking a break now because I've been talking for over 4 hours. So would start the next session by 4. Okay, so those that are presenting the next session, I think Marian is in the house. Then we have Joy Kareko and we have Anissa Tolapade. And so these guys will be presenting in the third session. So thank you very much, Samuel, for that presentation.
Thank you,